Before we dive into the microscopic trenches, let's map out the territory. Our journey today follows a specific path of understanding. We begin with the raw frustration of the forced upgrade cycle, specifically looking at the divergent philosophies of Intel and AMD. We then move into the anatomy of the CPU itself, analyzing the specialized roles of pins from power delivery to high-speed data lanes. We will explore why reserved pins aren't a magic bullet for future-proofing and how the invisible monster of power delivery often kills compatibility before a single line of code is even written. Finally, we will look at the human element, why manufacturers prioritize the simplicity of a new builder over the complexity of a seasoned veteran, and how signal integrity and BIOS limitations create a ceiling that only a new socket can break. Let's address the elephant in the room. When Intel announces a new LGA socket, the internet erupts. The common narrative is that these companies are greedy. We see Intel changing sockets every 2 generations like clockwork, while AMD's AM4 platform lived a long, legendary life. But to understand the why, we have to stop looking at a motherboard as a simple tray and start seeing it as a nervous system. When a manufacturer decides to change a socket, they are making a bet on the future. Intel's philosophy has historically been one of clean breaks. They argue that by changing the socket, they can optimize the electrical pathways for specifically new architectures. Is there a profit motive? Of course. But there is also a stability motive. If you try to force a high-performance 2024 engine into a 2010 chassis, the transmission is going to explode. In the world of PC building, the transmission is the pins. Imagine for a moment that you are shrinking down to the size of a dust mite, standing on the surface of a CPU socket. You are surrounded by thousands of golden pillars. To the naked eye, they all look identical. But in reality, this is a highly organized city. Every pin has a name and a job. There is no such thing as a generic pin. In a modern LG A1700 socket, there are, as the name suggests, 1700 contact points. Some are ground pins, acting as the safety net for the electrical current. Others are the VCC pins, the main arteries bringing the lifeblood of electricity into the silicon. If you lose even one of these, the CPU might still run, but it will be unstable, crashing the moment you try to render a video or launch a game. This specialized nature is the first reason sockets change. If a new CPU architecture requires a different voltage regulation or a different grounding pattern, the physical map of the pins must change to prevent a short circuit that could literally set your processor on fire. Now, let's talk about the data pins. These are the high-speed messengers. Some of these pins are hardwired directly to your RAM. Others go straight to your graphics card via the PCI Express lanes. When we moved from PCIe 4.0 to PCIe 5.0, the amount of data flying through these pins doubled. You might ask, why don't they just put extra pins in there from the start and leave them empty? Manufacturers actually do this. These are called reserved pins. They are the empty rooms in the CPU house waiting for a future guest. However, this is where the future-proofing dream hits a wall. You can reserve 10 pins for a future technology, but what happens if that technology requires 20? Or what if that new technology requires a level of shielding that the old pins don't have? You cannot update the physical spacing of pins via a software download. Once the copper is laid in the board's destiny is sealed. This is perhaps the most critical part of the story. Most people think a CPU upgrade is about speed, but for the motherboard, it's about juice. As we push for more cores, moving from 4 cores to 16, 24 or more, the power requirements haven't just increased. They've transformed. A motherboard's VRM, voltage regulator module, is like a power substation. It takes the high voltage electricity from your wall and steps it down to the tiny precise voltage the CPU needs. If you put a modern, power-hungry i9 into an old budget motherboard from 5 years ago, those VRMs would overheat in seconds. They weren't built to handle the transient loads, the sudden spikes in power that modern CPUs demand. Even if the socket was the same, the motherboard would be the bottleneck, leading to thermal throttling where your expensive new CPU performs worse than your old one. As we reach speeds of 5.0 GHz and beyond, electricity stops behaving like a simple flow of water and starts behaving like a radio wave. It creates noise or interference. This is called signal integrity. Newer motherboards aren't just about the socket. They are about the layers. A high-end modern motherboard might have 8 or 10 layers of PCB, printed circuit board. These layers act as insulation, preventing the data going to your SD from interfering with the data going to your RAM. Older boards with fewer layers simply cannot maintain the clean signal required for modern high-speed standards. This is the hidden reason for a motherboard upgrade. The very physical material of the board has to be higher quality to support the speed of the chip. Let's be honest, BIOS updates are terrifying for the average person. If the power goes out while you're updating your BIOS to support a new CPU, your motherboard becomes a very expensive paperweight. Manufacturers know this. They also know that for a new builder, someone putting together their first PC, the experience needs to be plug and play. If a beginner buys a CPU and a motherboard that are compatible on paper but requires an old CPU just to perform a BIOS update to make them work together, that customer is going to have a miserable experience. By changing the socket, manufacturers create a physical lockout. It's a way of saying, this board is guaranteed to work with this chip out of the box. It reduces tech support calls and ensures that the entry barrier for PC gaming remains low enough for the hobby to grow. In the end, we have to accept that the PC is not a static object. It is a living ecosystem. Socket changes are the molting process of the technology world. To get to the next level of performance, to reach the realms of AI processing, 8K gaming, and instantaneous data transfer, we have to shed the skin of the old standards. While it hurts our wallets in the short term, it is the only reason we aren't still stuck with the limitations of the hardware from a decade ago. So, how do you navigate this world without going broke? My advice is the 2-generation rule. Most CPU leaps within a single socket change are incremental. You rarely need to upgrade from an 11th gen to a 12th gen Intel, for example. However, when you jump 2 or 3 generations, the difference is transformative. To save money, don't chase every new socket. Instead, buy a high-quality motherboard mid-cycle and ride it out until the performance gap between your current system and the new ones is so large that the motherboard replacement feels earned. Also, always look for motherboards with BIOS flashback buttons. This allows you to update the board without a CPU installed, mitigating the compatibility trap we discussed earlier. As you look at your current PC, ask yourself this. Is your desire to upgrade driven by a genuine need for more power, or is it the FOMO of a new socket design? Have you ever successfully hacked an old board to fit a new chip, or did you learn the hard way that the pins always win? I'd love to hear your horror stories of bent pins or BIOS failures in the comments below. Let's learn from each other's mistakes. I wish you all great health, stable overclocks, and low temperatures in your digital journeys. If you found this deep dive into the socket wars helpful, please consider subscribing to the channel and hitting that notification bell. Your support allows us to keep demystifying the complex world of hardware, one pin at a time. Until next time, keep your thermal paste fresh and your cables managed.